So our last speaker of the day is Andrew Elvey Price, and he'll be talking about counting lattice walks by winding angle.
Okay, thank you. So I'd like to start by thanking the organizers for giving me the opportunity to speak here and also organizing such a nice conference despite the slightly difficult situation. Okay, so yeah, I'm going to talk about counting lattice walks by winding angle. So what that means is, as usual with counting walks, we want to count walks from some starting point so we want to determine the number of walks ending at each point according to their length. But since we're counting by winding angle, we also care how much they wind around some point. So in this case, the blue point. So, yeah. And so this is equivalent to counting walks on this spiral lattice, since the spiral perfectly takes into account the fact that we care about winding around a point. Okay, so questions like this have been solved at the large scale in probability and physics literature. I mean, in physics, the results are generally non-rigorous. But so these have been worked on for a while, but there were no exact results until Tim Budz work in 2017 and as well, yeah, and also this work. So, yeah. So I just also want to mention a couple of places where it's come up in the real world. So, for example, they could model if a drunk person walking around a corkscrew-shaped car park, such as this. And they also do a good job of modeling this situation where a dog's random walk can cause its leash to get wrapped around nearby objects. You can see here that there's even a lattice that the dog is walking on. Okay, so I should say a bit about Tim Budd's results. So Timothy Budd counted enumerated walks by winding angle on the square lattice. His method used matrices which count certain paths in, matrices counting certain paths in the lattice and eigenvalue decompositions of those matrices. And the solutions he found involve the Jacobi theta function, which I've defined here. So he got a variety of nice corollaries from his results. So this work my work uses a completely different method. I get a slightly different set of results on the square lattice, but more or less the same. So more or less I'm solving the same problems. But the main thing is that my method works on 3 further lattices other than the square lattice. So here are the 4 lattices that that I've counted walks by winding angle. So as I said, on the square lattice, this was solved by Timothy Budd. But yeah, so I'll mostly focus in this talk on the Kreweras lattice. Okay, so I'll just start with a preview where I give a very specific version of the results. So in this more specific problem, we're counting walks starting at the red square and ending at one of the orange squares, ending at any one of these 3 squares by length and winding angle around the blue point. So on the left, we count these with the generating function ETS. And so the contribution of each walk is t to the power of the length of the walk times s to the power of the number of places anti-clockwise around the point that the walk winds. So this gets an s squared because it winds 2 places anti-clockwise. On the right, we get an s inverse because this walk winds 1 place clockwise around the blue point. And so yeah, we have this generating function E of ts for what I call the self-centered case and E tilde of ts for the vertex-centered case. And this is how the series begin. Okay, so in this case, we have this very simple looking solution for the 2 generating functions. So each yeah, so these are in terms of the series tk, which are closely related to the theta function. So you can see from this sum that tk of uq is just a power series in u and q. Yeah, and so this expression defines t as a series in q, or equivalently by taking inverses, it defines q as a series in t. And so then these are the expressions for ETS and E tilde of TS. Yeah, so you can see now that Q is a series in T, these are each series in T and S. So this is the sort of thing that the solutions look like. And these could equivalently be written in terms of the theta function. It's just this way makes it more clear that it's actually a power series. Okay, so I'll start by talking about, so as I said, I'll focus on the Kreweras lattice. So I'll start by talking about decomposition of the lattice, which leads to functional equations for counting the generating function. Then I'll talk about how to solve the functional equations using Jacobi theta functions. I'll then talk about some corollaries and finally some analysis of the solution. Okay, so yeah, so as I said, we're counting walks on this directed lattice, which I call the Kreweras lattice, by length and winding angle around this blue point. So the first step is to decompose the lattice in 3 pieces. And so really, given that we're counting these by winding angle, you can think of this as breaking the spiral lattice into an infinite number of pieces. And so I'm not joining this piece to this piece. Okay. And so if we separate these pieces out into a sequence, then we're counting walks in this infinite sequence of pieces where the bottom of each piece is sort of glued to the left of the piece on its right. Okay, and so I'll just transform these so that they form squares. Okay, and so now I finally can define the complete generating function that I'll use to count these walks. So how it works is we use this generating function q of t, alpha, x, and y, which counts walks with, so here t counts the length of walks in this space, x and y, so each walk gives a contribution with x to the power of the x coordinate of the final point, y to the power of the y coordinate of the end point, and alpha, and e to the I alpha to the power of the, well, a factor of e to the I alpha to some power depending on what section the walk ends in. So I'll just give an example. So if we have this walk, this has length 10, e to the 10. It ends at coordinates 1, 3, so we get x times y cubed. And since it's in this section, we get an e to the minus I alpha. So the contribution of this walk is this. And similarly, to determine the generating, or the generating function q is defined as the sum of the contributions of all walks in this space. And note that q00 is e to the I alpha because, so that's where you set x and y to 0, because this just counts walks which finish in the bottom left square of the section that they end in, which is equivalent to the generating function I defined at the start, counting walks that end near the blue point. Okay, so to get generating functions for, to get a functional equation determining this generating function, we just consider the type of the final step of the walk. So if the final step doesn't jump through one of the walls, then it's either a northeast step, a west step, or a south step. And so in the case where the final step is a northeast step, we get this contribution because qxy is the generating function for all walks, and then we multiply by an x, y, and t for the last step. And similarly, we get these contributions in the cases where we end with a south or west step. The reason why we had to subtract a y here, for example, is that the blue walk can't end on the left of its section if the following step is a west step. Okay, so these are sort of the normal contributions that would come up if we were just counting walks confined to the quarter plane. And then we get these more complicated contributions from the cases where the final step is through one of the walls. So I'll describe, so that's these two contributions down the bottom. So I'll describe how these contributions come up here. So the first one, the e to the I alpha t q0x, comes from the case where we jump through the left wall of a section. The reason being that, so we get an e to the I alpha, of course, because we jump to the section on the left. So that multiplies by e to the I alpha. But we also have to notice that the new x coordinate of the position after jumping through the wall is the same as the old y coordinate. So that's why we have to put an x in the y position of q. Okay, so similarly, the last part of the equation comes from the case where the final step is through the bottom wall of the section. And so in that case, the new y coordinate is one more than the old x coordinate. Put the y in the x position, and we have to multiply by y. Yeah, and then we get an e to the minus I alpha because we're moving to the section on the right. Okay, so after getting this decomposition, it's not too hard to come up with this equation. So then the difficulty is solving the equation. So before I describe that, I'll just say a bit about why the other lattices, work. So the reason is that in each of these cases, we can decompose the lattice into congruent sections, rotationally congruent sections. Okay, and so that makes the same method work. So the same thing happens in the vertex-centered case where we're winding around the vertex of the lattice. And so, yeah, as you can see, again, we can decompose these into congruent sections and get functional equations for the generating functions in the same sort of way. Okay, so anyway, this is the equation for the Kreweras lattice, which we want to solve. So I'll start by rewriting the equation. So the first step is to take out all the factors of qxy and put them together into this polynomial we call the kernel. So this is the kernel here, and then rxy is called the remainder. It's a common method called the kernel method. And so the idea is we want to sub in values of x and y that send kxy to 0, because then r of xy is also 0. And r of xy is simpler because it doesn't, than the original equation, because it doesn't involve q of xy. So everything in the equation just depends on x or y. Okay, so the important thing to see here is that there's some function x of z such that k of xz, x of z plus pi tau is 0. So and there's some tau which depends on t that makes this equation occur. Yeah, so I won't describe why that happens exactly, but it's fairly easy to prove if just using the fact that it will have to be an elliptic function because it depends on the theta function. But anyway, so we get this equation for a certain explicit function x of z. And so then since we have this is equal to 0, it means that r of xz, x of z plus pi tau is also 0. And so this is the new equation we need to solve, where r of xy is given by this. Okay, so we need to solve this. then you can see if we substitute the definition of R into the, if we substitute x of z and x of z plus pi tau into R, then we'll get terms such as this, like q of x of z0 and q of 0 x of z. Okay, and so we define a of z like this, a of z and b of z like this, and so the new equation that we need to solve becomes this expression just depending on a and b. So we need to solve this for a and b. Now I haven't told you all of the everything we know about a and b, so we can also prove that they satisfy certain properties such as being almost even, so they're fixed under certain transformations. And so using these properties, we can solve the equation. So I just wanted to point out the important thing here is that in the parameterization of like replacing x with x of z and y with x of z plus pi tau, it's important that we're using the same, that we can use the same function for both, just at shifted values at the input, because it means that that we end up with the same functions in the final equation. Okay. So anyway, this is the solution we end up with for q of 0, 0. That I couldn't fit the expression for q of x, y on the page, so I'm just writing the expression for q of 0, 0. So if you recall, tau was defined implicitly by this equation relating it to t. And so, yeah, this ends up being a series in t and e to the I alpha. Well, it's not totally obvious from this expression that that's the case, that it's a series in the two variables. And so that's why it's nice to write everything in terms of these series t, k, which are related to the Jacobi theta function. And so this is the expression I showed near the start. Okay, so I'll now move on to a corollary of the results, which involves counting walks confined to a cone, such as this one. And so walks, just for a bit of background, walks confined to cones have been considered in a lot in the literature, particularly in the quarter plane. And so the idea is we take some cone defined by an opening angle alpha in, it's a multiple of pi on 2. So in this case, alpha is 3 pi on 2. And we take some set of steps, it's a subset of these, and then count walks which are only allowed to use steps from the set S. Okay, and so so in the quarter plane, these have been extensively studied. Mani Busquet-Melou started the systematic study of these walks in about 2005. I should remember the exact year, but oh well. And so they proved that there were 79 different step sets, 79 different non-trivial and non-symmetric step sets. And finally, after years of study, these step sets have, or the problem for each step set has been solved and classified into the standard complexity hierarchy. So in some cases, the generating functions are algebraic, some cases they're much more complicated. Okay, so that's for alpha equals pi on 2. For alpha is equals pi, the questions are fairly easy because we're just counting walks in the half plane. And so there's really only one variable that you need to care about, which is the height. For alpha equals 2 pi, the problems have all been solved as well. And so the sort of current area of research is alpha equals 3 pi on 2, the current main difficulty. And so in this case, the problem had been solved for 12 of the 74 different problems between, and I'll show those on this slide. So walks in the 3/4 plane, there are now 14 solved problems, including 2 that are new in this work. And so you can see these are the, 6 now papers that have contributed to those solutions. Okay, and interestingly, so far, for every problem, the complexity of the generating function is the same as that in the 1/4 plane. So just as a side note, an interesting question is whether that will always be the case. Okay, but anyway, so I'll describe, one nice aspect of this work and also the work of Budz is because it's based on walks by winding angle, it also allows us to count walks in larger cones, so the 5/4 plane or the 6/4 plane, 7/4 plane. And so that you can think of those as taking quarters out of the spiral that I mentioned, that I described at the start. Okay, so I'll describe how to, just with an example, how to count walks with this step set in the 3/4 plane. So that's this on the left, which is equivalent to the picture on the right, which I'll go into more detail about. So equivalently, we want to count walks in this space, which avoid the green and blue lines here. And it's going to be convenient to fill in the whole lattice here. So the way we do this is using something called the reflection principle. So the idea is that we consider, instead of counting walks that don't pass through these lines, we count walks that do pass through the lines. And then for those, we reflect everything in the walk after the first intersection with one of the 2 lines. So you can see that here, reflecting the walk in the blue line. And so if we do that, then we can pinpoint the endpoint as just the reflection of the old endpoint in the line that we reflected in. But more specifically, we can also describe the new winding angle in terms of the old winding angle. And so this is the way that the winding angles transform. So for reflection in the blue line and reflection in the green line. Okay, so in general, like for either of these transformations, if the winding angle is a multiple of 10 pi over 3, then the original winding angle, then the new winding angle will be a multiple of 10 pi over 3 minus 4 pi over 3. Okay, and so what that means is that if we count walks, so this expression counts walks which have a winding angle of 10 pi over 3 that do pass through one of the 2 lines. The second expression in the second line counts walks which have a winding angle of pi on 3 plus a multiple of 10 pi over 3, which have to pass through one of the 2 lines. And so the difference is just the walks which have winding angle or multiple of this, which then has to be 0, which don't pass through the either of the 2 lines. Okay, so we get this equation for walks, for excursions that don't pass through either of these 2 lines, which is what we wanted to count. And then we can just write that just by substituting various values for s as a finite sum of specific values of the generating function. Okay, and so this is the explicit value for walks by winding angle, for excursions in the cone. Okay, so now just a little bit of analysis. So since we have an exact solution for walks by winding angle and now walks in various cones, we can get the asymptotic distribution of the winding angle for random excursions or random walks. And so this is the density function after rescaling by log n times some constant. We can also get very precise asymptotics for counting walks in, say, a cone. And so we get this, which, so everything except the constant term was again found in probability literature by Denisov and Bartel. And finally, we can get conditions under which the generating functions for walks in cones simplify. So in particular, for walks on the Kreweras lattice, we have the generating function for these walks is algebraic, if and only if the opening angle is not a multiple of pi. And in the cases where it is a multiple of pi, the generating function here is d-finite, meaning that it satisfies a linear differential equation. Okay, so finally, just some further problems. So walks by, so it would be nice to count walks by winding angle with any allowed step set. It would be nice to be able to count walks by winding angle potentially around multiple points. And there are many more questions that have been addressed in probability and physics literature that would be nice to solve exactly. Okay, so thank you.
All right, let's thank Andrew for his excellent talk. And I'll pass it back over to Guy for questions.
Okay, there is several questions that I missed, I think. Jiayuan asked, does that data solution method apply in models with more congruent sections or incongruent sections?
Yeah, possibly. So, right. So I've been working a bit on this, and it gets more complicated in any case. So you can still, so you would need to write more generating functions than just the one that I used. So, but it's, yeah, it's not clear. It would get more complicated in any case.
Okay, I guess this was a related question. Sergi asked, oops, can you use your method to count walks on spaces formed by gluing quadrants together in more complicated ways? So I guess it was quite related questions to that one that you asked.
Yeah, so not necessarily. Okay, so there's a specific example, for example, on the lattice of points. Okay, yeah, so I don't know. I mean, you could write generating functions for trying to count those types of walks. And I mean, it may work because fundamentally something about the method works, but there's always just a question of whether you'll actually be able to solve the transformed equations. So you should be able to write functional equations. You should be able to transform them to something involving theta functions, because the kernel, in all of those cases, the kernel will be, you'll be able to characterize the kernel with theta functions. But yeah, whether the transformed equations can be solved is hard to know without trying.
Nicholas asked, can you compute asymptotics for arbitrary S?
Arbitrary S. Yes, yes. Yeah. So usually it will just have a simple pole. Well, okay, I'm sure I haven't looked into every specific value of S, but yeah, what will happen will depend on the value of S. But yes, essentially you can.
Maybe one more question. Thomas asked, on the Kreweras lattice, can you avoid a larger triangle in the center?
Yes. Yeah, so you can avoid a triangle of, well, I haven't gone through the details, but you can for any specific size of triangle. I don't know, like if you'll get a nice formula for an arbitrary size, but essentially, yes.
Okay, perhaps we can ask further questions on the Slack, and I will pass it on to Christian.
All right. Please stick around for our coffee break today if you're all interested. But before that, let's thank Andrew and all of today's excellent speakers one more time.